All right, welcome back. In this video, we're going to discuss, as you see, the fluorescence presentation from the second week of lecture 4. We're going to only start covering the material. There's quite a bit to review, so this is just the first video of a few. We're going to touch a little bit about the introduction of that whole subject, and also what is the whole thing with the Jablonski diagram, which is super important to understand. Not only is it well represented in questions, I have seen more than once an instance in an exam where they asked to draw it. So we're going to do just that as well. Let's get started. This is a copy-paste from Wikipedia, and I always say that I don't really like to use material from Wikipedia as much as other people, but I do find their definitions very easy and comprehensive. So fluorescence is the emission of light by a substance that has absorbed light or other electromagnetic radiation, which is essentially somewhat redundant. Electromagnetic radiation can be considered as light. So what we need to understand is that there are molecules that are fluorophores. Fluorophores are molecules that can absorb light or electromagnetic radiation and emit light. That is specific characteristics of that specific molecules. And different fluorophores can absorb different spectrum of lights. Each fluorophore has specific wavelengths that they can absorb. That's called their absorption. The absorption spectrum. And accordingly, they have a specific spectrum that they can emit light in, and that is called the emission spectrum. The emission spectrum. You will also see oftentimes the absorption spectrum referred to as the excitation spectrum, which is really the same thing. What's important to understand is that if I have this fluorophore here, and I know that this fluorophore can absorb light and emit light, what I also need to know is what wavelengths of light I can shine on this fluorophore to get back that emission. It's important to understand that you can't excite a fluorophore molecule with any wavelength of light. It's specific for every molecule. Let's just say this specific molecule can be excited with blue light and would emit, let's just say, a green light. This is a specific character for this specific fluorophore. And that's really what we're looking at understanding. And we're going to talk a little bit more at length about absorption and emission spectrums later on. All right, so let's keep going and talk a little bit about the Jablonski diagram. I'm going to talk about it at length and make sure it's very well explained and well understood. Just to touch base with you what I mean, I'm talking about this little guy right here. And all the other sub-depictions, this depiction, this depiction, this depiction, this depiction, it's all the same diagram. It is the Jablonski diagram. And that diagram is the essence of fluorescence, of understanding what is going on. We already know that we can use light, or we can use photons to excite the molecule. And namely, we excite the electrons in the molecule. Electrons are excited. The electrons absorb the energy. Absorb the energy. Never follow my footsteps as far as spelling. What I'm going to do right now is I'm going to draw the Jablonski diagram from scratch, mainly because I find it easier for other students to look at diagrams that were freshly constructed, and also being that they sometimes ask for students to draw it, so I'm going to do just that. I drew the base level here. This is the ground level, or noted S0. This is the level at which electrons are ideally at and will aspire to get to. This is the stable level. And I'm going to have several excited levels. So say this is my first excited level, and this is my second excited level. Now, we already discussed these are electronic transitions. And also in between them, in between these electronic transitions, we have rotation and vibration levels as well. Meaning that the molecule, the fluorophore, can lose some energy in vibration or rotation, and not only having electrons jump back and forth in electronic transitions. And those are the lines that you see Let's look at those lines that you see here. And these lines basically fill in the gaps between these electronic transition levels. Perfect. So we have the first excited level, the second excited level, and I'm going to just work with these two before I get into the other type of levels that we have. But essentially, let's see what's going on. Let's just say I have my electron. It's green right here, and I had a photon of light that is in the absorption spectrum of the fluorophore, which means the fluorophore can absorb it. And that electron shot up, got excited, got some energy and shot up. And now it's shot up and it's right around here. The interesting thing is, and this is an important idea, is that as soon as electrons get excited, the first thing that happens after they get excited is that they rotate or vibrate down to the closest level, or the closest set electronic level. Let's just say that this electron shot up here. The first thing that would happen is that it's going to vibrate and rotate down to get to this level. You can consider these level an intermediate semi-stable levels, and the electron is not going to be able to stay in these intermediate rotation vibration energy levels. It's going to have to get to one of these electronic set levels. And it's quite important to label this, so we're going to do that. This is called internal conversion. And internal conversion follows a rule, and it's quite important to understand because they often ask about this rule, Cash's rule. And it's just the same thing I just stated, that an electron would always aspire to get to semi-stable set level after being excited. This is essentially the internal conversion is a follow-up idea or the implication of Cash's rule, and that's important to understand. Now after that, my electron is, you can say, has some potential energy at this point, and we always said that these electrons would aspire to get back to the stable ground level. I'm going to just label this here. This is the ground level. All right, this is the ground level, and these are the excited levels. I'm going to just put it here. Excited. Perfect. Now, when we go down from a higher level to a ground level, we know that we're emitting energy. And that energy could be emitted as a photon. So if this little dude drops down here, it can emit a photon. Let's just say this is the color of the photon. And this photon would be in the emission, within the emission, always within the emission spectrum of that specific fluorophore. Whereas the photon that was exciting the fluorophore would always have to be within the absorption spectrum. And this is important to understand. Perfect. So I have my specific molecule was excited by a photon within the absorption spectrum of that specific fluorophore. One of my electrons dropped up, got excited, got some energy. Because it was in the intermediate vibration rotation levels, due to Cash's rule, it rapidly vibrated or rotated down to the first closest semi-stable level here, the semi-stable excited level here. And then after a while, and these are very short times, and we're going to mention what time frames we're talking about, this dude just dropped down and emitted the energy as a photon. And it's important to understand that this emission of a photon is called radiative relaxation. And just so you know what I'm talking about, this is perceived as KF. This is K fluorescence. This is the relaxation as far as fluorescence. And the KNR, the dropping down in the KNR, refers to a non-radiative relaxation, which means that we can have this little electron drop down and not emit a photon. This would be a non-radiative, or we're going to refer to it as non-radiative K, non-radiative form of relaxation. But it can also emit a photon, which is obviously a radiated form of relaxation. So we mentioned these transitions. Let's mention some time frames. And again, you would see these time frames cited slightly differently in different websites and articles, but the gist is the same. It is really quick. The absorption happens really rapidly, around 10 to the negative 15. And the internal conversion also happens very, very rapidly, 10 to the negative 13. And just to make it obvious, I'm talking about seconds here, 10 to the negative 15 and 10 to the negative 13 seconds. And we can have fluorescence, we're talking about radiative fluorescence relaxation, at around 10 to the negative 9 seconds, just around there. And now we understood that if we have a fluorophore that is excited by a photon that's within its absorption spectrum, one of the electrons is going to shoot up, it's going to get excited, essentially it's going to store some energy, it's going to lose some energy in internal conversion in a non-radiative fashion, and that's also something I should have mentioned. Internal conversion is rotation and vibration, it's non-radiative. We would not get a photon from internal conversion. And then it achieved a semi-stable status here in the first excited level. And obviously this can happen in the second excited level or the third excited level or whatever, and emitted a photon here. What's important to understand also is that if I have this electron here, let's say it's the same electron, it went through internal conversion, what it can do here, it can also vibrate a little bit and then stop here, and that from this point emit a photon. It's important to understand that the vibration rotational levels are intermediate levels that the electron can go through, and this is at random, entirely at random. What we also need to bear in mind, that if we have a photon that was emitted from this energy level, and a photon that was emitted from a bigger energy level, a bigger difference, this is going to be a more energetic photon than this. Or rather, this is going to have a higher frequency or a lower wavelength than this photon. And this should make sense because the more energy is associated with the transition, the more energy the photon is going to have. Okay, fair enough. So what I'm going to do now is I'm going to incorporate what we have left to talk about. And what I'm going to draw right now is what we see here, this side. And understand what's going on this side too. And it's always important, and I would encourage you as well to take your time and just draw the Jablonski diagram just a couple of times. It helps it set in your mind, it helps you understand it, and if need be, in an exam or a self-control, you'd be able to draw it. And we're gonna name these again, just to hit the point home. We have the ground state, we have the excited states, S1 and S2, and then we have the triplet state. And this is what's denoted here as the T1 triplet state. Okay, and it's also associated with vibration and rotational levels. Okay, and this is quite important to understand. Well, we have that. Perfect. And obviously it has vibration rotational levels up above it, up below it, so I'm not going to really draw all these lines all the way through, but you can just imagine. Now, what may happen is that I was excited by a photon within my absorption or excitation spectrum, and I gained some energy, and I got to this level right here. I'm going to go through internal conversion. I'm not going to label it again, you can imagine, and it's already labeled in that one slide that I showed you. So I'm going to go through internal conversion and get to this point. Another possible transition is called, and this is the triplet transition, or the forbidden, this is called a forbidden transition as well. We're going to touch on that in a second. Why is it called forbidden? Now what may happen is that this electron can move to this state, the triplet state, that is in a slightly lower energy level than the excited state that we have here. It's still an excited state, still has energy, but it's slightly in a lower state. And this is called inter-system crossing. Inter-system crossing. And it crossed that way. And from this point, a few things can happen. In the same way, it can vibrate all the way down, or rather go down in a non-radiative fashion, non-radiative fashion, means that I'm not getting a photon, or it can also come down in a radiative fashion. And if it comes down in a radiative fashion from this triplet state, it is going to be called phosphorescence. Phosphorescence. And phosphorescence is considerably takes longer, or has a longer lifetime, you can say, than these lifetimes here. And again, it's cited very, very differently in different places, but I would say right around 10 to the negative 3 seconds to even 10 seconds. So you can appreciate that this is considerably slower than these transitions, exponentially slower. So this is the phosphorescence. And again, phosphorescence, you can think of it as slow fluorescence. But phosphorescence and fluorescence are terms that are not interchangeable. Phosphorescence only occurs when there's a radiative relaxation from the triplet state. And phosphorescence is considerably slower. And I'm only reiterating this because you may encounter this same specific questions and variations in your self-controls and your finals. So phosphorescence, I'm just going to put it here, although I went through this radiative. Perfect. Now, another thing that may happen is that even though this electron went through intersystem crossing, intersystem crossing, it can go back from this triplet state. It can go back to here. And this is also called intersystem crossing, meaning that intersystem crossing could go either way. I can go down here to the triplet state, or the forbidden state, and I can go back via intersystem crossing to my excited state. If that happens, if I go back and forth, same thing can happen when I'm here. If I'm here, I can go down in a non-radiative fashion, okay, just like this thing right here, non-radiative. But if I come down in a radiative fashion, we already agreed it's going to be called fluorescence. But this fluorescence is going to be called delayed fluorescence. And why is it called delayed fluorescence? Well, instead of going through the internal conversion and just rapidly giving me a photon, it went back to an intersystem crossing, back and forth to the excited level, and only then did it emit a photon. So it took its while going through transitions back and forth, so it's delayed fluorescence. And delayed fluorescence obviously is radiative because we're talking about a photon. And it can go to intersystem crossing and back, and also come down in a non-radiative fashion. Any of these transitions can occur in a non-radiative fashion. And also, like we mentioned, it could be a mix of non-radiative and radiative emissions. And any emission that I would get, any radiative relaxation, any photon I would emit is always going to be within my emission spectrum. So for any given fluorophore, I know what kind of visible light wavelengths I may expect it to emit. And this is quite important to understand. Now about the triplet state. And it's only very, very slightly represented in the minimals. What's a triplet state? What do they mean? But basically, I'm just going to touch base on the main idea. We know that electrons have spins. And we know that if I have an orbital, this is my orbital. Let's just say I have 2 orbitals or 3 orbitals. Let's just say this is my p orbitals, right? I have 3 p orbitals. And if I put electrons in them, I'm putting electrons in them in this fashion, just following the rules. And these rules say, first of all, you're only going to house 1 electron in 1 orbital before you start doubling them up. And when you double them up, it's really important that their spins are anti-parallel to one another. And this is the stable, we can say, right way of housing electrons. But when the molecule is in its excited state, and we'll go through that, it's very subjected to many various forces that apply to it. And those forces can cause the shuffling of these electrons into a forbidding way of mixing them in their orbitals, causing what we call the triplet state. And what they say, or the way they depicted it in the presentation, is right here. There's just the difference between the singlet state, which is parallel and anti-parallel in the same orbital, to various situations which may not occur. And being that they violate the laws, they are called forbidden. But this actually takes place, even though it's called forbidden. That's really all I would make a point to knowing about the triplet state. It may be something that pertains to the minimal itself. And being that we already mentioned going through the minimals, a very important minimal is this one right here. What are the possible ways of relaxation of an excited electron in a molecule? And this refers to what we just went through. A lot of times, or rather, it wasn't the second self-control in 2011, that a lot of students saw this and did not associate it with fluorescence. They're like, okay, it can vibrate down and it can relax down, maybe emit a photon, but they didn't associate it with all these different variables that we went through. This intersystem crossing, internal conversion, vibration, rotation, non-radiative fashion, radiative fashion, phosphorescence, delayed fluorescence, and this is what I mean. We have vibration and vibrational relaxation, internal conversion following Cash's rule, intersystem crossing back and forth from and to the triplet state, the forbidden transition, fluorescence, which is radiative, phosphorescence, also radiative. It's very slow fluorescence, but don't mix these two. Fluorescence and delayed, phosphorescence and delayed fluorescence are not the same. We only get fluorescence when we get radiative relaxation from the triplet state. When the triplet state radiates down, it's always going to be phosphorescence, even though it's considerably slower. And whenever I radiate down from one of my excited set states, is going to be fluorescence. So please don't mix these fluorescence and phosphorescence and delayed fluorescence. And obviously, there's energy transfer to another molecule. We're going to touch base on that when we talk about FRET. And just in case you're wondering, should I be remembering all these? This is kind of a little bit crazy. But if you draw the Jablonski diagram a couple of times, you'll notice that all the possible alignments of the transitions are going to be evident to you. As well as far as I remember, they only asked for 5. So 1, 2, 3, 4, 5 would be enough, even though you should know these 2 as well. So this is pretty much all that I'm going to cover about the Jablonski diagram. Hopefully, I've made this a little bit clearer. I did, in fact, in my idea, cover all the material that is relevant to understanding the different transitions here. Make a point to drawing this a couple of times, drawing the possible transitions, labeling the axes. I'm not sure if you should be remembering the time frames, because when I went through the course, they said that it's important, but they never asked about it. Just stick to the minimals. Hopefully you found these useful, and I'll see you in the next video.